All right. So, good afternoon, everyone. So today I'm going to talk about the project that I've been working on for a long time now, and the topic is about personalization, and more specifically about scalable infrastructure for such a thing as personalization. And it all started with an IRC grant about 6 years ago now, and is EIT ICT project for 2 years now. And so we have been, highly sponsored by the ERC and EIT ICT labs, and also more recently on the academic part, we got a Google Focused Award. So I'm local. I'm running a team called ASAP here in Rennes. Okay, so just this is pretty much our life today. So we are kind of surrounded with a large number of data all over. We go to social networks, to collaborative platforms. We navigate the web and everything. And well, basically, it's easy to say that we can be quite overwhelmed with these kind of things, and there is a crucial need for personalization. So there is already a large amount of personalization tools around us today, but it's still growing, and I don't think that there is any other way around now than to try to filter out the data that we have. So what have we been doing in this area? So it all started in 2008. And the project that we got at this point, which was called Gospel, was about trying to personalize user navigation over the internet. And it was quite different at the time, in the sense that, first of all, you have to remember that at this point, there was not a lot of personalization around. I mean, we were talking 2007 when we wrote this proposal. And it was very seldom to see this word around at that point. Now, the originality of this project was that it was based on peer-to-peer. So the goal was to be able to scale using some peer-to-peer paradigm, which is basically no server kind of infrastructure, and also to provide some form of privacy, because with such infrastructure there is no big brother kind of server, and then you can run any application with just the help of the user machines. So obviously, when it comes to personalization, one thing I should start with is that you need to gather a large amount of information, and potentially sensitive information about the users. Now, there are other privacy problems with peer-to-peer, and I won't have the time to come to this, but we also took care of those. Now, in 2000, at the end, well, almost a year before the end of the project, basically, we started to think that the algorithms and the tools that we provided in the context of peer-to-peer were actually making a lot of sense out there, and not only in peer-to-peer systems, but also in the cloud infrastructure. So at that time, I got an ERC proof of concept project, which is a follow-up project for innovation with the ERC, and also a project that is called was called at the time Allyours, with the IIT ICT labs, and we had a partner here, which is Trying to Rise, with which we had some living lab kind of experiments. And at that time, we were, and we still do in a way, we were pursuing two things. One was a peer-to-peer recommender, and the other one was a kind of a generic tool for any web content provider, basically, to provide recommendation, which is the main focus on the startup that we are thinking about right now. So this provided with a number of funds for engineer, and we still actively work on this kind of project. So we hope to have this startup created by the end of the year. And recently also we got support from Google in the form of a Focused Award on the academic side to continue working on these kind of things. So I'm first going to give you basically a flavor of what we do in the ERC first, so on the peer-to-peer side, and I would like to show how we can actually leverage these results in the context of cloud, and more specifically of a startup. Okay, so basically there are many ways you can achieve personalization, and I'm not going to go into, I don't have the time to go into all the way you can do it. But working on a k-nearest neighbor is actually a very good way to do personalization. So basically what that means is that you have a set of, say, users, and the goal is to find the closest users to any other user. And this is called k-nearest neighbor. So the goal is to find the k-closest neighbors, basically. Now, this has been used not only in on the web and in navigation, but also in data mining, image processing, and so on and so forth. Now, to find this, there is also another set of approaches to do it. What we focused on was collaborative filtering. So collaborative filtering is the fact that you basically leverage the activity of some users to help towards your own activity. So again, in this context, you can do it in different ways. You can, so basically on the internet, what you can have is data, so what I call items, or users. Okay, so you can center your research of closest neighbor on the items, but you can also center it on the users. Now, most of the approaches out there focus on the item KNN. We focus on the user. Now, the reason is, one of the reasons why items have been preferred is that it's a well-known thing, and I mean all experiments confirm this, that there's much less items out there than there are users. So basically, it's much more tractable to go for content. And when you have to deal with an extremely large amount of information, you spend less time if you want to find the connection between items and users. Now, because we were specifically targeting peer-to-peer infrastructure, it was actually making much more sense to leverage user information so that every user can actually take care of her own action and her own data. So this is what we did. So basically, the whole, pretty much everything we do is, take a given user, so in that case Bob, and basically try to find the k-nearest neighbor in the world, okay? And you can use, once you have this topology in a way, you can see this is a graph, so this is a topology. You can use this for personalized notification, which we did, and you can use this for also recommendation, which we also did and still do, and many other things. Now, so basically, I got this from a talk that I heard recently from a professor at MIT, and they really have the sense of marketing. So we don't want to deal with big data, but we want to deal with truly big data, okay? Meaning that there is an enormous amount of information, and I mean, it's no news that it keeps increasing. And what I want to advocate, and what I believe is a good way to think about this, is that if you really want to scale, starting as we did, a little bit by chance at the beginning, but it turns out that it's a very good idea, is that if you want to scale, you can just try to think peer-to-peer. Because when you design a peer-to-peer algorithm, basically what you have to do, there is no way that one given machine can actually, track the entire world. So you come up with algorithms where there is, every node basically has only a local knowledge of the system, of the data out there, right? And then based on the individual actions, you come up with a global, an algorithm that provides some global service, okay? In that case, k-nearest neighbor. And because of this, and because it is designed in a peer-to-peer way, so that you restrict yourself to have a local knowledge, basically you can scale. And no matter how much the data grows, you can still scale. And this is really, I think, the key to what we're doing right now. And basically that works out very well also for the KNN graph construction, in the sense that a naive way to do k-nearest neighbor search is to try to exhaust the database, okay, and try to compare any item user to any other item user in the system. So if you want to, designing in a peer-to-peer way, and actually most of the centralized solutions right now do not look exhaustively either, but they sometimes have some form of centralization, you basically want to try to compute similarity with a restricted set of pairs instead of everything. And this is exactly what we do by considering at each iteration when we try to build this graph with a partial set of candidates and a specific sample. And again, the way this sample is constructed is very important for the convergence time that you have. Okay, so basically, when you want to do it in a peer-to-peer way, what do you do? there are two things that you want to decide. So which are the nodes? So consider that you have a system of, I'm calling nodes, but it's basically users here. And what you want, the first thing that you want to know is which nodes are close to each other, okay? So when it comes to images, for example, that can be a very complicated process. When it comes from user, you can also have a very complicated metric, but this is not the core of what we're doing. And actually what we're doing can be adapted to pretty much any similarity metric that you can come up with. As long as you can deal with local knowledge. So basically you need to have a similarity metric, which is whenever you have a pair of two users, you can tell how much they are close to each other. Now, the second thing, which is extremely complicated in the context of a peer-to-peer system, is how do you find them? Okay, it's not only you don't only need to know to recognize them, but you need to find them in such a very big world. And this is what you do with sampling approaches. So with respect to which nodes are close to each other, the only thing that, and I'll present a few results in the context of this talk, and we use very similar, very standard similarity metrics, which have been used out there for a large for a long time. So just consider, for the sake of this talk, a very simple model where you have a bunch of users, some items, which can be URLs, for example, or any items that you can have in the database. The profile of a given user is just a vector of items that she liked or bought or looked at or these kind of things. Take your favorite one. And the good thing with this is that you don't even need to look at the content, right? So you don't need to have some semantic associated. It doesn't mean that it's not useful, and it is, right? But in what we're doing, we don't use it, and that makes the approach extremely flexible in a way. Right, so that was for who is close to each other. Now, the thing that we wanted to do, and that's one of the results that we came up during this project, is how you can build such a topology of close neighbors in a fully decentralized way. Again, fully peer-to-peer means no server, okay? So the first thing that you need to do is that you need to connect all the users out there. And the way we do it is by having an underlying infrastructure here, which builds a random graph, okay, uniform random graph, and that keeps updating. So I'm not going to go into the details because I don't have the time. But basically, this graph it relies on gossip-based algorithms where periodically each user has a sample of other users, say a uniform sample, take it from here, and then periodically it picks one of its neighbors and exchanges the neighbors with each other. So it means that you keep reshuffling the graph this way. What is good with this is that not only it keeps connectivity and it makes you make sure that you get rid of the users that are not online anymore, but also it gives you a very good way to sample the network, okay? Because if you wait long enough, say the order of the size of the system, you will have seen everybody, okay? So then it's very easy to pick your closest neighbors. Of course, if you do this, as I said, the complexity would be the size of the system, which is not what exactly we want to do. So on top of this, what we do is that we build an additional layer where we speed up the convergence by having a specific biased sampling, in the sense that, so say that the two users are already close to each other and are known to be close to each other. Basically, the neighbors of one are very likely to be also good candidates for the neighbor of the other. That's the only, and that speeds up the convergence very quickly. And then basically you can converge from a very large system in a very small amount of cycles towards a topology, which is, in that case, a mix of a random graph topology, ensuring connectivity, and the k-nearest neighbor topology. Once you have this, you can actually do a lot of application, and we did a number of applications. So starting from news recommendation, but also you can do top K queries, you can do geo recommendation and search and any other things, okay? So these are the kind of academic results that we had on this. And I'm going to focus on the decentralized news recommendation because this is the beginning of this story of this thinking of a startup. So at this point, what we wanted to do is that we wanted to have a service in which, in a fully decentralized way, you would have some news, an application of news, and you would like a system to recommend news to user without any intervention, a specific subscription from the users. So basically, a user just keep going, liking. Of course, you need an input, so the input would be I like that news or I didn't like that news. And then by using this, the user will have a more more refined set of news appearing. And as the system learns from the user, basically you are supposed to have better recommendation. So you can see a little bit the interface as this. So there is this trend of news, and then there is some recommended items that you can get on the top. So you can see this as an implicit notification pub-sub system in a way, notification system, without subscribing explicitly to, say, sports or whatever. So that means that, for example, I'm sure that many of you right now are interested in the World Cup. Okay, maybe in a month you won't be interested in football at all. So basically the system can actually capture very quickly the thing, because you haven't ever subscribed to football or to the World Cup, but just because your friends are very fond of it, then you will get news, and then you can tell the system that you like it at the time. So how does that work? Well, that was called WhatsApp. So this is why it's WhatsApp, which was a very bad name. I mean, it was a very good name, but many other people have kind of the same ideas. So, it's no longer a useful name. So basically, this is all guided by the user opinion. So there is two things. The first thing is that because the user likes or dislikes the news, then that goes into the profile, and this is the way that the topology is generated. Okay, so the KNN selection is basically building the topology. Now, of course, and then the user opinion also influences dissemination, and we have a novel kind of dissemination protocol where basically whenever a user likes a news, then it is disseminated to her friends, and when it doesn't, it is disseminated to somewhere else in the system in order to give a chance that news to go somewhere else in the system, okay? Now, so that influences the dissemination. What is very tricky here is that basically the network obviously influences the way the topology is done, because you use this topology to disseminate news, and the other way around, the way that dissemination is done also influences the topology, okay? Because if you're not careful enough and you keep sending the same news to the same set of people, they will become closer and closer and closer and get isolated from the network. So this is why when you're in a peer-to-peer system, you have to be very careful with these things. And this is what we do with our dissemination protocol, which does some orientation. So who should I send a news when I get it? Well, the thing is that when you like it, you will send it to your friends, really like a collaborative filtering approach would do. But one of the different things that we do is that when you don't like it, you still forward it to somewhere useful in the system. Now, in addition, you don't use it in the same way. So we know that, if you send in a very large system of n nodes, if you send it to log n nodes, you will have a very high probability that everybody gets the news. Now, you don't want to do this for everything, because when you don't like the news, you don't want it to be spread everywhere. So basically, you do this in your cluster when you like it, and you just send it to a very small amount of other nodes, in a very small indeed, because in that case it's one, when you don't like it. So that just gives a chance to the news to travel somewhere in the network. And actually, I don't have time to show you the results, but that turns out to be about 30% of the news that got somewhere in their dissemination path a dislike operation. So that's a useful thing in a decentralized system. So just to give you a little bit of what we compare with this, so gossip is just a sort of flooding kind of mechanism, where you would send the news to all the other nodes that you have in the system. Cosine collaborative filtering is just that you do something when you like a news item. Otherwise, you don't do anything. So what matters here is that there are two things that are important. One is to what extent you receive the news you wanted to receive. This is a recall. The other thing is to what extent you have some noise in the process. So how many news that you didn't want to receive do you receive, and that the ratio between the number of news that you receive and the number of news that you like that you receive. This is precision. Because obviously, and that's the case of gossip, the best way to send to someone everybody she wants to see is to send everything to everyone. Okay, so this is why precision matters in that case. So what we can see is that we do much better. I mean, this is the average. So that's a real data set, a small data set, but a real one. a survey that we did on a bunch of friends and family. And what we see is that, so this would be the average precision that you would have for any two users in the system. So basically we improve on this, while also improving on the recall with respect to a standard collaborative engineering approach. Okay? So just to conclude on this part, which was more of the academic part of this project, I would say. So personalization is a good thing, and decentralization is healthy for several reasons: scalability and privacy. Again, we came up with a number of approach for privacy, because in that case, privacy matters between two users. Okay, you don't want to hide from a central server, but you might want to hide your profile from other users that are in the system. So obviously I won't have time to go this, but you can try it. There is an operational prototype of this. Now, at this point we said, well, that is actually a nice application that, and you know, when you talk about this to people around you, and not only computer science, people are like, yes, that would be very nice. And actually the first test that we did, people got very excited about this. So we said, well, maybe that makes sense to actually go further and try to make a product out of this. So that was the first idea, like, you know, news recommendation. And it turns out that all these algorithms that we developed in this context, again, as I said, they make obviously a lot of sense in a peer-to-peer context, but they do make a lot of sense in a centralized context and in a cloud computing context, in the sense that they're just very scalable algorithms that you can implement whatever, okay, in hybrid architecture, in central infrastructure, whatever, and using the same kind of things. And in that case, that becomes kind of a generic tool for personalization. And this was our second idea. So at this, when we started this ERC proof of concept project, as well as the EIT ICT lab project, that was the idea. We would pursue two directions, with peer-to-peer direction, which is very sexy, but at the same time, on the business side, not extremely easy to develop. And the one which is a generic recommendation platform to achieve personalization, basically, to pretty much any website that you have in mind. And we did a development experiment. And in the context of this application specifically, and also on the centralized, but still on the news recommender part, we did some experiment with the partner that we had in the project, which was Transferrise, and which still is, because this is a project going on right now. Now, in the context of the generic recommendation platform, we had a lot of effort for the development and also beta test, like, you know, trying to find some client/beta tester to see how the whole thing behaves, and to what extent people like it, and also trying to work out the business model, because at the end of the day, this is what you want to, you know, when you want to have a viable startup, you really want to take care of this as well. So I'm just giving you, 2 minutes flavor of the experiment that we had in Transferrise, because that was part of the EIT ICT project. So basically, there were 138 users from the desktop. So Transferrise is a lab in which they have real users, and they have some incentive to have real users and make them use the system. So these are experiments from real user, basically, and that was interesting. So basically, well, this is a distribution of age, and this is a distribution of jobs that there were. What we got from this was basically the usage part of it, because when you peer-to-peer, at least our prototype, you have to install an application on your laptop. So sometimes that can be cumbersome or not. So that was the kind of thing that we were looking at, whether people were happy to install it, and, you know, were using it, and basically they used it, but that doesn't work, because, you know, when you go into this real life prototyping, you have some bugs, unfortunately. And this is also the kind of usage that we have, whether, you know, people were happy. Oh, that's okay. This is still in Italian, because, but you can figure out what it means, right? So basically, you know, to what extent? So people were, you know, generally quite happy with the news they received. Actually, we had a slightly different programming way of injecting news in the system between the mobile version and the desktop version, and results were a little bit different, but they were quite happy. Also, we got some user interview they did some interview of users, and interestingly enough, for example, whereas we were very proud to say that, you know, that was a generic platform and everything, when using the system, it was funny that some of the users said, well, you know, we would like something like a more social kind of a platform and everything. And actually one thing that I didn't mention here, but on the peer-to-peer thing, one thing that really was striking is that the fact that some users were offline impacted quite a lot actually the register. So that was all the kind of things that we had in mind. So basically, and that wasn't a surprise, some people are afraid of peer-to-peer, and for some of them for good reasons, like business is not that good when you're in a peer-to-peer system, and sometimes for bad reasons, like, you know, for some reason you're happy to give away all your data, but having a, you know, piece of software installed on your laptop sometimes freaks out people. But anyway, my point here is that's not my point. What I want to say is that when you're afraid of peer-to-peer, you can still design with peer-to-peer in mind, and I think it's a very good way to do it. And actually, that came up with our kind of focus of the startup would be the cloud-based generic recommender that we have in mind. And the goal of this is to provide a tool which is extremely easy to install. It comes in a widget, basically. So it's just a line on your website. And the goal is that it will track history of users, come up with a nearest neighbor search, and then provide recommendation, which is a parameter of that line. Okay, so it's very easy to install. You can install it on pretty much everything. And because data are stored on our servers, you can actually leverage the activity of users across multiple applications. Okay, now, what is different from what exists out there is that it's user-based, and because we have a very, I wouldn't say, well, efficient algorithm, then you can do it real time, okay? And that's very good to actually capture the dynamic changes of interest of your users across time, okay? So we don't have a large offline, we do have a bit of offline stuff, right? But as opposed to many recommendation strategy which do offline and then provide some recommendation at some point, we can actually do it very quickly because we have an efficient algorithm to do it, okay? Right, so basically you can use it for different things. So you can increase the number of pages that you will see on one side. You can also do some traffic transfer between websites. So if this is, and we, by talking to people, this is really something that some people want to do, like they have different websites. One of them, say, is a normal website, and the other one is a premium website, which means basically that you can sell your ads at a higher price on the second website. So it actually makes sense to transfer some traffic from the first one to the second one, okay? And this is something you can do within the same company, because there are many companies out there that have several websites with these different characteristics, but you can also do this with different company, and then it's called a little bit publicity, but it's a slightly different way of doing it. So we can do cross-application recommendation, and also because it's such a simple it's such a simple tool to install, basically pretty much any website can do it, okay? So you don't need to be Amazon anymore or to be any very big company to do it. You can just install this widget, and actually from our website you can install it and run it very easily. And the other thing that we have actually is that we have a tool for doing some implicit user segmentation using this specific algorithm. Okay, so basically what is important on this slide, because I'm kind of running out of time here, is that this is extremely easy to install. So if you're running a website, just, you know, be my guest and try it. So this is just the initial results that we got. So this is a website on which one of our beta tester basically. So this is about 3 million unique users. They have this website of general, you know, content edition website, and they also have some shopping kind of website. And the goal, the eventual goal would be to transfer do recommendation from the basically shopping kind of items, okay? Now, this is a probability to predict the next click. Okay, so basically what you can see is that with this number of neighbors here, as soon as you reach 100, which we can do pretty easily, okay, basically you can have a very high probability of being able to predict the next click. So this is offline analysis, okay, we kind of replay the simulation. And this comes, well, I'll come back to this slide later on. So basically this is better than popularity, which is, you've often seen on website like the most shared or the most viewed or the more whatever. So obviously this is a better way to predict your next click than others. So what is our status right now? We have about 6 to 10 clients. It depends whether you count on website or company as a whole. Beta tester right now. Some of them are huge. They have an extremely large amount of traffic, so that was quite a bit of a challenge. And actually, turns out to be, we had to work out a lot on the scalability of the infrastructure. Well, luckily, we are distributed system people, okay? And this is where that kicks in, this expertise kicks in the sense that we can do it. And actually, when it comes to making this scalable and trying to know exactly what we should put in memory, what we should put on disk, we were able to do it. So that's kind of a nice side effect of this expertise, and we are in the process of evaluating our technology. So to ask me to give some kind of lesson or experience that I learned on the way. So first of all, it's I would say, but that's no news, no surprising news for anyone in that room, I guess. It's a long process from a research prototype. You can be quite happy with a research prototype. When it comes to being able to make a client happy, that's another story. The other positive thing, so it takes a lot of time. Another thing which is positive is that really I think that in research we have this ability to pioneer some kind of work. And again, I really believe that in that sense, we were very pioneer in the ideas that we had back in 2007, and that turned out to be extremely, relevant technology right now. So that's something, we can shamelessly say that we're in a good position to do these kind of things. Now, the key success that factor, I would say, is that trying to reach out potential clients is something which is challenging. Probably should have put challenges rather than. Well, that's the same, basically. If you address correctly these challenges, I would say this is a key to success, I guess. It's how to reach out potential clients, because this is definitely a different job, okay? Because the clients are not our peers that would be amazed by some lovely plots and numbers and everything, but just want something to work, and to work quick and fast and without messing up with their website. So that's something that is crucial. Now, trying to whenever you want to sell your technology, try to talk in a different way. And I'm coming back to this slide here, which is, working the impact. Yes, 1 minute. Okay, thanks.
Because I would like to give the floor to the audience for questions.
Okay, sure. Oh, okay, this is what I missed, you see. I thought 30 minutes, sorry. Is that, for example, here, the impact of the number of neighbors, something that in any research paper would be of the highest importance, right? Well, clients don't care. I mean, if you tell them this is 100 that you need, well, if you can do it, you just don't mention it. So I guess the last thing I want to say is that the evaluation against competitors is very difficult and very different from what we're used to, because you don't know how they work, and we don't know what they have in their core engine, and that makes it very difficult for us to say that we are the best. So unless, you know exactly the algorithm. Thank you very much, and I apologize.
No, it's okay. Thank you, Anne-Marie. So I promised you high tech. You had high tech. Any question from the audience? And the mic will.
I'm standing between, the session and the coffee break, so I guess. So.
Can you ask a question to the previous?
Sure. Sure.
Tuha? All right. She'll answer for everyone. My question is, on the cloud computing, we have it's a moving bridge. We have to catch up with people, the technology is on and keeps moving every day. We have the use the user who is like, as soon as they get to use to something else comes up. What's being done to not leave people behind? Second question for you, is there a way someone can contact you and get your technology to use in some other softwares?
Say that again?
Your algorithm.
Yes.
I have like an idea I'm working on, and recommendation is something part of it, but can it be used just to take the technology, or you have to use it yourself?
No, I have to use it myself, yeah.
Okay, so you can share. It should be peer-to-peer technology.
But I'm happy to discuss anything during the coffee break. Thank you.